The term function, as representing it here, came into existence in the 18th century in correspondences between Bernoulli and Leibniz, talking about how they could represent and discuss the equations that they were working on, where in particular a very successful student of Bernoulli's, Euler, defined a function in 1748 as a function of a variable quantity is an analytic expression composed in any way whatsoever of the variable quantity and numbers or constant quantities. Which isn't very helpful. It's a definition, but it's not a very good one. Thankfully, he would get a little bit better by 1755, where he would a bit more clearly state, when certain quantities depend on others in such a way that they undergo a change when the latter change, then the first are called functions of the second. This name has an extremely broad character. It encompasses all the ways in which one quantity can be determined in terms of others. So, in this way, using that definition, we can think of a function as instead being some sort of mathematical model for describing a special kind of relationship, a special kind of dependence. And as a result, when we insert the notation of equations and look at this as functions in the mathematical sense, we can think of the x values of an equation like y equals x plus 2 as being something like our inputs. Those are what we call the independent variables, and they have that name because they're the values that we have freedom to be able to vary, to be able to change as we see fit, as we want to understand what's going on with the function, while the y values are what we get out from the input x's. Those are our dependent variables as a result because they depend explicitly on what we do with x, where any number of things can define a function, something like if we just made that x squared, if we looked at y equals x squared plus 2, that's another function. The first one was linear, the second one's quadratic, and we'll talk more about that later, but they still work a lot of the same ways we've seen. However, not every nice, well-known, commonly defined equation has to be a function. And in fact, there are a lot of things that, even though we might want to work with them for various reasons, aren't functions. The most famous example is something like x squared plus y squared equals 1. For those of you that don't know, this is the equation of the unit circle. And we're going to get a graphical way to describe when something isn't a function. It'll be pretty easy to tell in that case, but more generally, if you want to be able to see if something is or isn't a function, what we can do is try and solve it for y, where in this case, if we try and solve that for y, we would end up with y is equal to plus or minus, that should be a 1 there, 1 minus x squared, because we can get multiple values for y coming off of a single value of x as a result of that ambiguity from the plus or minus. So this, even though it's a very elementary equation, it's a very important equation, is not a function, at least not in this way that we're looking at it. Where now that we have some more of a sense of what functions look like as equations, as well as where that idea comes from, we need to define our notation just a bit more carefully.